Let's try another example of solving a linear system of differential equations. This example is going to be y prime equals 1, negative 2, 2, 1 times the vector y. So again, we want to find all of the eigenvalues and then the eigenvectors. So I'm going to take the determinant of a minus lambda I. So that is the determinant of the matrix 1 minus lambda, negative 2, 2, 1 minus lambda. So that actually becomes 1 minus lambda quantity squared, and then minus a negative 4. That's actually going to be lambda squared minus 2 lambda plus 1 plus 4, so that's plus 5, and we're going to set that equal to 0. Now you cannot factor that, and so what we're going to do is use the quadratic formula to see that lambda in this case is equal to 2 plus or minus the square root of 2 squared, or 4, minus 4 times 1 times 5, and that's all going to be divided by 2. So that's 2 plus or minus the square root of 4 minus 20 is negative 16, and then we're going to divide by 2. So that's actually 1 plus or minus I times the square root of 16, which is 4, and then divided by 2 is 2. So essentially that's 1 plus or minus 2i. And so we can see that our eigenvalues here are complex. So let's see what we get when we're dealing with complex eigenvalues. So what I'm going to do is I'm going to let lambda be 1 plus or minus 2i. And then note that I want to solve the system a minus lambda I. So a minus 1. And then where I had a plus 2i, I'd have a minus 2i. Where I had a minus 2i, I'll have a plus 2i. So negative 1 minus plus 2i times the eigenvector v is equal to 0. So what does that system look like? Well, I need to take 1 minus lambda in that upper right corner. So 1 minus lambda is going to be a negative or positive 2i. And then the negative 2 in the matrix remains the same. Then the 2 remains the same, and then I'm going to get a negative or a positive 2i. And so that is our matrix. Our right-hand side of the equation is going to be 0, 0, and we want to row reduce. Now, that's going to give me, the first row is going to remain negative, positive 2i, and then a negative 2, 0, 0 on the right side. And then I'll notice that if I take the second row and I multiply it by plus or minus 2i, so here I can multiply by plus or minus 2i and then add the rows together, then I will get a 0. And then plus or minus 2i times a negative plus 2i, that'll give me a positive 2. And so I'll add those together and I'll get 0. So essentially, the second row is a multiple of the first row. And so I get a row of zeros. Okay, so what's my eigenvector going to be? Well, what I'm going to do is I'm going to start with the second component, and I'm going to get it to match. There's already a negative 2 there, so if I multiply that by a negative or positive I, and then I multiply the first component by 1, then that indeed is going to be the eigenvector. Just take this row, multiply it by that column, and you will get 0, 0. And so what I'm saying is that the eigenvalue 1 plus 2i corresponds to the eigenvector 1 negative I, and the eigenvalue 1 minus 2i corresponds to the eigenvector 1 plus I. And so what's interesting here is the eigenvalues are complex conjugates of each other, the two different eigenvalues, and then the corresponding eigenvectors are complex conjugates of each other. And that is a fact that we will state at the end of this example. So let's just look at one of these eigenvalues and eigenvectors and see what happens to the solution. So we get y of t is equal to e to the 1 plus 2i times t, and then the corresponding eigenvector is a 1 minus I. Well, that is a complex function, e to the 1 plus 2i times t, times a complex eigenvector. But I know that my solution is supposed to be real. I'm assuming that I'm going to be modeling physical systems that have real answers. So I want to express this as a real function. So how am I going to do that? Well, I'm going to rewrite e to the 1 plus 2i times t as e to the t, so e to the 1t, times, and then e to the 2it is cosine of 2t plus I sine of 2t. And that gets multiplied by the eigenvector 1 minus I. So let's see if we can do that multiplication. So there's going to be an e to the t, and then 1 times cosine 2t is cosine 2t. And then what I'm going to do is I'm going to multiply I sine 2t times a negative I. And what that's going to give me is just sine 2t. And so there I have a sine 2t. And so that's kind of the real part of this solution. But there's also going to be an imaginary part. There's going to be plus I times, and then again I have e to the t times sine of 2t. That comes from multiplying I sine 2t times 1. And then I also have I times a negative cosine, or a negative e to the t cosine of 2t. So I get that by multiplying my cosine 2t times the negative I there. Now I made one minor error here that it's not really an error because it is correct, but I do want to factor out e to the t. So I'm going to go ahead and factor out e to the t here. So this becomes I e to the t times sine 2t negative cosine 2t. Okay, so what I've done is I've taken y and I've split it up into real and imaginary parts. So the e to the t cosine 2t sine 2t, that's the real part. And then the I e to the t sine 2t negative cosine 2t, that is the imaginary part. Now, you could go through the whole process again for the other eigenvalue and eigenvector. So if you repeat the process, for lambda equal to 1 minus 2i, and then the v, the eigenvector, is going to be 1i. If you repeat that process, what's going to happen is, in fact, you will just get the negative. So you will get the complex conjugate of this solution. So instead of plus I e to the t times that vector, you'll get minus I e to the t times that vector. So now what I'm going to do is I'm going to define two solutions. So I'm going to, first of all, think about y as being y plus and y minus. And then I'm going to define y1, one of my solutions, to be a half times y plus y minus. So I'm going to take half of one of the solutions and add it to half of the other. If I do that, I just get the real part. I get e to the t times cosine of 2t sine of 2t. So this ends up being the real part. And then if I take y2 and I make it 1 over 2i times y plus minus y minus, what I'll get is the imaginary part, e to the 2t times sine 2t negative cosine of 2t. So this is the imaginary part. And so what I'll get, though, is two real solutions. Okay? And these two real solutions are linearly independent. You can use the Wronskian to show that, and I encourage you to do it. y1 and y2 are going to be linearly independent. And so the general solution, if we do that, is going to be y of t equal to c1 e to the t times cosine 2t sine of 2t, and then c2 times e to the t sine 2t, and then cosine 2t. And so now I have a linear combination of two linearly independent solutions, and they're both real. And so I've come up with a real solution to this problem. So there are some important facts that we need. Okay, the first important fact is that if lambda is a complex eigenvalue, a plus bi, with eigenvector v, then the complex conjugate lambda bar, which is a minus bi, is also going to be an eigenvalue of that matrix with an eigenvector v bar, the complex conjugate of v. The second fact that we proved is that if my solution is of the form u of t plus I v of t, then both u of t and v of t are linearly independent solutions to my differential equation. So here, my solution looked like a real part plus I times an imaginary part. And then we saw that the real part was a solution and an imaginary part was also the solution. And so this is the method to solve a linear system of differential equations where the eigenvalues are complex.